Okay, welcome back everyone. So today is a continuation from the previous video. And again, this time it's about linear differential equations. Well, that was our end goal for both videos, but here, last video we just discussed the basics of differential equations, the necessary terminology and a practice initial value problem, and that should get us ready for actually solving these linear differential equations. So let's see. So first I want to define something called standard form, and that's going to be, and from now on, instead of dy dx, I'm going to be usually using y prime. So standard form is y prime plus some function of x, and we're supposing this is a continuous function times, well, y equals another function of x. Call it g of x. Okay? So now, what we're going to do is we're actually going to define this function. So this is where it kind of gets weird. We're going to define a function with the following property. It's called mu of x, and it has the following property. Is the property that mu of x times f of x spits out mu prime of x. Okay, this might seem arbitrary, but in fact, this we can find some function mu of x like that has this property for any continuous function f of x. Hence the condition that f of x is continuous. Okay, so we're going to worry about computing mu of x in a second. For now, let's just actually continue figuring out how to solve this function as a function of x in terms of as a function of x. So we're going to have y equals some function of x. So how do we do that? Well, what we're actually going to do is we're going to multiply both sides of this equation by mu of x. What does that give us? That gives us mu of x y prime plus, and then we're going to use the fact that mu of x times f of x is mu prime of x. So that gives us mu prime of x y. And that's just going to be equal to mu prime of, mu of x g of x. But the beautiful thing is here that this is a product rule. It's a product rule of the two functions mu of x times y. To be more clear here, if we work from this side to this side, it takes the first function, the derivative of the first function times the second function, plus the first function times the derivative of the second function. That's exactly product rule of these two functions. So this is equal to this again, right? Mu of x g of x. And now we can integrate both sides with respect to x. So when we integrate both sides, well, again, the integral is an antiderivative, so it undoes the derivative by part of the fundamental theorem of calculus. We're going to skip the specifics here because I assume you've already taken single variable calculus. So what we get, and calculus 2, or integral calculus. Anyway, if we integrate both sides, we'll get mu of x y equals the integral of mu of x g of x dx plus some constant, right? This is the resulting constant from this. This is the resulting constant from this integral. Okay. Okay. I guess I'll call this C for now. So I'm going to divide both sides by mu of x in order to get our desired function of, in order to get our desired explicit solution. So it's just going to be this integral. I wrote my mu very strangely there. Dx plus C all over mu of x. Okay, so now our goal is to figure out how to compute mu of x. Well, to do that, we're going to go back to this definition of mu of x, the property that it satisfies. And we're going to divide both sides by mu of x. So we have f of x equals mu prime of x over mu of x. But notice that this is actually just the derivative. So this is just the derivative of the natural log. Hold on. Of the absolute value of the natural log of the absolute value of mu of x. Okay, because if we differentiate this, we're just going to get, well, 1 over mu of x, right? But then by chain rule, it's mu prime of x as well, multiplied by mu prime of x. Okay. Oh, I forgot the prime symbol. And now again, we integrate with respect to x. So we're going to get, and I'll call this new constant of integration capital K. So we're going to get the integral of f of x dx plus capital K equals ln absolute value of mu of x. Okay, so now this is where it gets kind of funny with the constants. I'm pretty used to this, but I'm not sure if you guys are used to this, so I'll kind of talk through it. If we raise e to both sides, that's normal still. And then we're going to separate these two terms by using properties of powers. So e to the integral of f of x dx e to the capital K equals ln. And I'll skip one step. This is going to be plus or minus, so it's going to be plus or minus this. So we're keeping the constants in one spot here. Plus or minus, that's just the definition of an absolute value. So that's just going to be equal to mu of x. Because, for example, absolute value of x, if we take a very simple case, absolute value of x equals 1, well, what are the solutions for that? That's plus or minus 1. So, yeah, this is the exact same idea here. So this is just one single constant. So the idea with relabeling this is that since it's one single constant, we can just scoop it all up in, I'll call it lowercase k. So this constant we're going to call lowercase k. It doesn't affect any computations. It's just that we have a different kind of constant that we have here. We're working with a different constant, but that won't affect any computations. So now we have this definition for mu of x. And, well, what we'd like to do is we want to get rid of this constant k, because since it's impossible to get rid of both constants, it would be nice to get rid of one, because, well, it's going to be really hard to compute this stuff if we have two constants to deal with. But we can do that fairly easily by plugging this back into our formula here. So that, and rewriting the constants. I'm actually running out of room, so I'm going to go down. I forgot to get rid of this stuff. So if we plug into there, we have y equals, and bringing out the constant k, k times the integral of e to the integral of f of x dx g of x dx plus c over k times, e to the integral of f of x dx. Okay, now I'm going to force factor out a k and then divide the c by k. And this is, again, using the same idea as relabeling. This is another constant. This is another constant. I'm going to call this, well, I'll just call it c, and I'll call this c1, so hopefully that doesn't confuse you guys. So I'll call this capital C. All right. So what do we get? We can also cancel the k's, and we're just left with y equals the following integral of, well, now since these two have to be equal, this definition, that tells us that, well, e to the integral of f of x dx equals mu of x. So in other words, our final answer for mu of x is equal to e to the integral of f of x dx. And again, another reason for this is that if we had our constant of integration here, that we called, if we add our k here, it would all cancel out in the end. Like, it would not help us in any way in the end. So, in other words, we can just ignore it right now. In other words, this is our final form. And I guess that would be it for this video, because that's, I don't know how I never mentioned this, but this is called the integrating factor. This is what we call this mu of x. So I guess the general process of computing, of evaluating such linear diffie-qs, is first, what you want to do is you want to compute your integration. First what you want to do is you want to convert your ODE into the standard form if possible. Usually the problem will tell you to solve this with the integration factor or something, or whatever. So you'll know that you can put it in this form. And the idea is to just get this 1 in front of the y prime term, function of x in front of y, and a function of x in, over here. This could be a constant, doesn't matter. Still a function of x technically. Okay. And then what you want to do is you want to compute your integration factor, and what you'll need for that is you'll need your f of x term here. Don't forget the sign. If it's a negative sign, you have to include that in your f of x term. So then what you want to compute is e to the integral of f of x dx. Usually this computation is fairly straightforward, but you have to be pretty careful with it. Okay, and then what do you want to do? Well, then when you multiply both sides of your standard form by mu of x, so by your integrating factor, whatever. Then what you do is, well, we have a general form for this. What the result is going to be on the left-hand side is this really beautiful result. That is, it's going to be the product, the derivative of the product of the integrating factor and y. So technically, you can just skip to this step. But I prefer going through the step of multiplication, since sometimes you might forget to have this mu of x times g of x on the right-hand side, which you'll end up with if you multiply both sides by mu of x. Then you integrate both sides, and finally you solve for y, and you have your constant here. And then maybe the problem will ask you to find interval of definition, but we'll deal with that in the next video. It's going to be a bit complex, but, well, not really. So I hope you enjoyed this video. Hopefully it was fairly easy to follow. I do these proofs because I personally don't like, for example, the channel organic chemistry tutor. He makes great study material videos. They're great for, practicing problems. But the reason I don't use him as a resource normally, if I'm not doing, practice problems, the reason I don't use him as a resource is because he doesn't go through any proofs at all, like no proofs. And then I just feel like I don't deserve to be using this theorem or whatever I'm using. If I just, went with integration factors, and I went with the fact that, oh, look, your integration factor is equal to e to the integral of the coefficient of your y term here. And then you want to multiply both sides by the integration factor, and then you get this nice product. It would all just seem, it still seems like magic, but I feel like I kind of deserve to use it now. Hopefully you feel the same way. It's kind of a weird feeling, but I hope you enjoyed the video nonetheless, and have a nice day. Goodbye.